that, that this thought scare you, you can still run for your life from the door. Okay, if you can live for an hour without seeing the source code, we will be talking about Python, of course. So, first of all, a very few words about the place I work in. It's called CRS4. It's a research center which was established in the first 1990s by the Nobel Prize for an idea of the Nobel Prize, Carlo Rubbia. And we do fundamentally three kind of things. We do research in ICT, we do research in environmental sciences and renewable energies, and in biomedicine and clinical research. So, what we'll be talking about? First of all, what exact field do we work in? And then what's the project? And why did we choose to use Python? And did it work well? And then brief glance into the future. Where do we go from here? So what field do we work in? Well, usually when you hear about biomedical research and clinical research, you'll think about lab coats, microscope, maybe brain specialists, but this is not the kind of thing my group does. We do have, for example, excellent genotyping facilities at CRS4, so we do that kind of, not brain specialists, but we do that kind of lab coats, microscope things as well. But my group's, which is called Healthcare Flows, deals with the ICT in medicine. So what kind of things do we do? Well, first of all, distributed medicine. For instance, teleconsulting. We have a system we are developing right now that allows cardiologist, a pediatric cardiologist, to visit his patients from a distance, and which is cool. And semantic and computational management, what does it mean? Well, we have a lot of data nowadays, of digital data, and healthcare is no exception. It's the so-called data deluge, lots of data, terabytes of data coming from genotyping, from clinical data, but the matter is how can we use data coming from different sources together? You have to have a conceptual model, a technological model to relate data coming from everywhere. So that's another thing we do. But the project I will be talking about is in the field of clinical system integration and traceability. What does it mean, traceability? It means you are able to follow the path of your data, of your processes. What are we doing? What did happen during my clinical process? And why is that important? Why do we bother? Well, there was a report by the Institute of Medicine in year 2000 that quite spurred the industry into caring about traceability because it presented quite ghastly figures, like this one. Each year, in the United States alone, 44 to 98,000 people die due to preventable medical errors. Think about wrong dose of chemotherapeuticals or wrong dose of radiation or just swapping transfusion blood bags. It's a huge number and it's scary by itself, but to better put things in perspective, I present here it besides other common death causes for the United States. So as you can see, it's actually easier, more probable to die for medical errors than for breast cancer, and 10 times easier to die from a medical error than from a motorcycle accident. So it's unacceptable. And so how do we solve the problem? Well, we are developers, we are ICT workers, so my first thought was, well, we could use computers. That's why we are developers, because we believe in the possibility of solving problems with the aid of computers. And there are studies, recent studies, that show a positive correlation between the use of ICT and the safety and the efficiency of care. This is one study carried out during 2 years in Texas, 41 hospitals, about 170,000 patients. So it's a big study. And it has found some correlation. So how much ICT are we doing at the moment in the healthcare sector? Well, I have this figure for Italy, which is 1 billion euros. Sounds like a very big sum, but it's not. Why? Because if you think about the dimension of the whole healthcare sector, it's about 7% of Italian GDP, which means more than 240 billion euros, which is, I think, nowadays a gazillion dollars or something. And this makes this a very small sum. And if you look at the figures, you'll see that actually healthcare is the sector where ICT is more underutilized. And not only in Italy, it's the same at European level, it's the same in the United States as well. So it's the hardest sector, and we don't do enough ICT. But there's more. How do physicians actually use computers? What for? And as you can see, they use them a lot for billing, doing invoices, for scheduling their appointments. And only the circled one has to do with clinical data. So that's cool, of course. ICT is useful for billing, but that won't actually help to lower that number. So not only we have to do more ICT, we have to do ICT for the right things, and there's more. This must be the scariest website I've ever seen in my professional life, except maybe Windows API, but that's another story. And this is a complete database of documented cases in which information technology errors had adverse effects, so-called adverse effects, up to death on patients. Think about a computer system that regulates the amount of radiation in cancer therapy. Too much radiation, you kill the patient. The opposite, you are not curing him, so you kill the patient as well. So how to do the ICT in the right way without it causing even more problems? Well, you all developer of open source language, so I'm sure I don't have to persuade you that standards are a good thing. Let's think about the internet. If we didn't have TCP/IP, what we would have today would be a number of very small networks, not interconnected, CompuServe and AppleNet, PythonNet maybe, who knows. And that's what you find usually in hospitals. Lots of small digital islands. This one talks maybe the language of one company and so on and so forth. But we do have work undergoing. We have, for instance, H level 7, health level 7, and the level 7 refers to the ISO OSI stack. So it's for application, for clinical applications. It's a global authority with members everywhere in the world, and they do standards for interoperability documents, and the main standards are called like the organization, which is convenient because one less thing to remember. And version 2 is a pipe text format separated by pipes. Version 3 is more XML-like. And so that's nice, but it's not enough, because we can have systems that can talk between themselves, and this is very important because you don't have to go in front of the monitor and write out stuff in paper and do data entry again, which actually happens, but it's not enough, because one of the most difficult things in the field of healthcare nowadays is that hospitals are a hugely complex environment. You have dozens of professionals from different backgrounds. Not all are physicians. There are nurses. There are our colleagues, of course, system administrator, and patients as well, which rarely are physicians. So a lot of persons trying to work for the same way and for the same reason. And of course, we have dozens of different processes. We have patient admission, we have surgery, we have ER, we have exams, and a lot of stuff to do. And you have to do that too in a standard way, because it's very important, the order in which you do things, the data path between systems when you do an exam, and so on and so forth. So there's another organization, IHE, integrating the healthcare environment, that does just that. You can see it has about 500 members. We are there in there. or industrial partner is in there, and so on. What they do is publish manuals, documents, they call transactions and profiles. From a developer's point of view, they're just huge collection of use cases. The very UML meaning of the word. They have actors, they have sequence diagrams. So if you have to implement something, laboratory medicine, you find the exact procedures in the manual, how you are supposed to do it, what message should be passed around, which is very important. So what's the project? Of course, we wanted to bring IHE standards and HL7 into the real world, into the clinical world. And where to start? As I've said to you before, there are dozens of different things that happen in a hospital. Where to start? You have to start somewhere physically. And so we started from this 6-7 times out of 10. What happens in medicine, especially critical decision making, which means do we do surgery, do we sever his limb, and so on and so forth. Of course, it's leveraged by laboratory exams. I think it has happened to every one of us. You go to the physician, she's not very sure, so let's do maybe this and this and this blood tests. And of course, if the data is wrong, the decision will be probably wrong as well. So that's where we decided to start. And we have some data about where the mistakes happen in this process. And you see, this is the core business. This is the blood or specimen being taken and analyzed. And it's surprising that only 1 error out of 10 happens here. Why? Well, because a laboratory is quite an homogeneous environment. It's full of the same type of professional lab technicians that are trained to do that kind of work. Most exams are performed by machines, by robots. And so over the years, just using common quality control techniques, it has become a very safe environment. But 3 errors out of 10 happen even before. 6 errors, sorry, out of 10 happens even before getting to the laboratory. How is that possible? I mean, we don't have the test. How can you be wrong? Is there a time machine? No. This is from a developer point of view what happens. Some physician says, okay, you'll have to do a glycemic index maybe or some other kind of test. And then we have the results. Of course, what's problematic is the part that's in the middle. It's called phlebotomy, which means taking specimen from your body in vivo, which could be usually blood, but not only blood. So what can go wrong? It looks quite simple. It's not. First of all, if there are systems that are not interconnected, there are a lot of typing errors. So maybe you are named one way, but the nurse types it's wrong, and there's patient misidentification. Or maybe just it's the general practitioner or the physician that just orders the wrong kind of test. And what can happen is wrong tube type, because not all tubes for blood are the same. They have different kind of chemicals depending on what specific test you are going to do, and which are identified by cap color. Try to notice that when next time you have your blood drawn. And can be clotting activator or heparin or lots of stuff. And if you take the blood into the wrong tube type for the wrong exam, well, at least you'll have to do the exam again, which could be dangerous if it was an emergency. Or if you're not that lucky, the error goes undetected, and the test, of course, will give wrong data. So, just some blood tubes. And another point of failure is labels. How can such a trivial thing like a label can be a point of failure? Well, the label is the union the path to tie together the physical world where the specimen resides and the data world. So what happens, for instance, is that it's written manually and you misread it, and whose blood is that again? Maybe you swap patients, so I'm positive and I become negative and the other way around. So the label is very important. So ocean areas, I won't go into detail, but they are just derived from IHE profiles. And so what's our solution? Here is the overview of our system. And you can see on the green ones, the green guys are hardware. Our industrial partner called Impeco, it's a group which was leader in laboratory automation, so they really know their way in medical robots and so on and so forth, has made two labelers, which are just robots that can process tubes, they can apply label in a very good way, they can print them clearly, they have sensor, for instance, to read cup colors. Wait a minute, this is pink, it is supposed to be red, you're wrong. And that kind of stuff. Of course, this is very good, but if this is the heart of the system, it can't really know what you are supposed to do, because, of course, it's red, but how can the system know it should be pink? Well, that's the job of this other part, the integration engine, which is the mind of our system. It's implemented using an open source software called Mirth, which does two important things. First of all, it translates between the laboratory information system, which could be vintage, have some old protocol. No matter what, it will be able to get the data out of it, maybe polling on a database table, whatever, and it will export standard compliant HL7 inside. So it's a translator, first of all. But then again, it implements IHE actors. It decides what message gets passed when an exam is inserted into the list. So it's the real mind of the system. And then we have apps, applications that are used by the nurses and by the lab technicians and so on and so forth. So at this point, why Python? Well, we had why and how. First of all, why? We had some requirements, of course, for this project, and I want to show you. First of all, we wanted our code to be very readable. Why? Well, because first of all, not all of professionals involved in this project were and are developers. There are, for instance, mechanical engineers doing the hardware part, and they're not programmers. So if you have readable code, you can use it to pass along ideas in a very precise way. You can do that if it's full of technical details like public-private implement throws and so on and so forth. And besides, this is in an environment, a field where code audits should be very frequent. Sometimes they are required, sometimes you just want to do them because it's better to do them. And as the shorter and the more readable the code is, the easier it is to perform them. Second requirement, agility. Why? Because in this field we have lots of standards and laws and regulations, and if you have a client from a new nation, you have to think things again, because you could have something new, and every hospital and institution has their requirements. And besides, we are a research center working with an industry. So if requirements change, it's positive, because it means we are exchanging our knowledge. They change their view of the problem, and we do as well. So we must be ready to change when it's needed. Third, portability, because in the real world there's a lot of stuff. Completeness. We had a lot of different ICT needs for a project of this scope, and we needed something that could have a lot of libraries, a lot of features. And last, ease of deployment. We don't want to have to keep track of 100 external packages, to keep track of packages being discontinued or not backwards compatible anymore. So as few as external libraries as possible. Let's have a see at the requirements. It does ring a bell, doesn't it? Those are simply Python's best features. It's readable, it's executable pseudocode. It's very agile and it's portable. It comes with batteries, we all know that. And because it comes with batteries, we don't have to keep track of a lot of external libraries. And then how? If you tried to get Python in the enterprise, you will going to find some resistance. Definitely, yes, I know you tried. And what kind of argument our partner or industrial partner wasn't so keen? What kind of argument did they use? Well, it's not Java. Oh, I know it's not Java. That's why I want to use it. So, and how did I counter this argument? Well, of course, you can show them the usual use cases. You see, Google uses it, and ILM as well. And yes, that works up to a point. What I did was just implement a first prototype of the system, which sort of worked. And then they were, oh yes, oh, this is nice, but you got this wrong, you got fix it. So my advice, what I call the first law of Python advocacy, is shut up and show them a prototype, a working prototype. Of course, it's not mine, it's Eric Raymond's, shut up and show them the code. And then this worked, because Python is very capable of promoting itself once they can see. We know how fast it is, they don't, so show them. And a few weeks ago, something happened that was beyond my wildest expectations. Some guy coming from the hardware staff, which is another city, came and said, oh yes, we're doing stress tests for components, we do them in Python. What? Yeah, it's so easy, you use for in range, and if not, it's easy. Indeed. And I didn't suggest that. It was Python. They have how. So that's the zeroth law of Python. So you already using Python. So how did it work? This is the part of the project in which we use Python, which is 90%. So I'll show you just a few snapshots around to give a quick idea. Hardware drivers. A lot of hardware, different systems, firmwares, and the barcode reader, and the printer, and whatnot. So PySerial, Python USB, there's a lot of stuff in Python. If there is not just UC types, we're talking about machines that have operational in bottlenecks, that is mechanics, because it's in seconds, so who cares about the overhead? We use the module struct, which is fantastic, and I'll have a lightning talk at 6:30 if you want to come. And so the nice thing is they had for free the Python shell, because we implemented all the low-level commands using struct, and we encapsulated them into a class. And then we did what Alex Martelli said in the keynote. We built over the first level that was one-to-one with hardware. We built second level and third level, higher level APIs. And so just opening the Python shell and instantiating the class, they had a console that could drive the hardware, which was very cool. Asynchronous messages in the networking. If you remember the project diagram, pretend to do. If you don't, there was in the middle something called a dispatcher that emerged from refactoring, because everyone was talking with everyone else, which is never a good idea. So we put this thing in the middle that passes message around and so on and so forth. And it must be done in a synchronous way, because the system can't just hang when you have an exam coming in. So how did we solve it? Twisted, of course. I think it's we're only about 30 minutes. Anyway, Twisted is one of Python killer apps. Once you get over the headache, you can actually write new protocols in minutes and in a few lines of code, which is very cool. It's non-blocking and asynchronous, and it means that it works the way we want it to. and it's very robust and quite scalable. That's why it's a club. And we could do another cool thing. As you'll see now, we decided to do web applications, and we had initially to package Apache, which is quite a deployment effort to do. But with Twisted, it was very easy just to get rid of Apache and serve Django stuff through it. With WSGI it's very easy to do. And you will have SSL, which is very important because we don't want patient data to go in the clear. And we have XML RPC and we have SOAP all for free. You just add subclass and you have XML RPC. So applications. Why we did web apps? Well, no deployment, no client maintenance, no working on Windows 7, Windows 98, Windows whatever. Just use a browser. Okay, just use everything except Internet Explorer 6, actually. And you can do pretty good interfaces nowadays with Ajax and that kind of technologies. And that's important because giving the users, the laboratory technicians, good feedback is key for avoiding most common errors. And we use Django, of course. It has an MVC, its own kink, its own kind of MVC actually, but you can separate models from views and you can reuse stuff, so it's very enterprise. And it's very useful even outside the web. We ended up using Django's ORM for other stuff as well. For instance, we used it to manage the tube labels, cap colors, association with chemicals and tube dimensions and so on, because you don't need everything of Django. You can just use as few Django as you want, which is why loose coupling is always a good idea. Just the opposite of ZOP. If you had the chance to use it, ZOP was this giant block of rock and monopolize your attention. Just some screenshots. They're quite ancient. It got nicer now. This is the application used by the machine administrator. There are a lot of data about what's going on at low level. And this is an example of what's the NARS, the phlebotomist, see when, in this case, when a tube is printing. And there's more because IHE does in Asia, in Europe, and in the USA an event called Connectathon, which principle is if your system is really compliant to standards, then you should be able to connect to other systems without knowing who they are. That's Connectathon. It's a blind connect. Everything connects with everyone, and in the end, you'll see what is really standard compliant. And apparently, our system, which has a lot of Python in it, was compliant. So we are certified as IHE compliant, and there's more. In this very moment, we're doing an experimentation for the machines, for the whole system, in the biggest hospital of Sardinia, which has more than 2,000 people in the staff, which serves more than 30,000 patients per year, and which is a very high-tech hospital. They have laboratory automation, and so this system is being used to securely do the blood drawing, the phlebotomy process in the hospital. So yes, it was a success. Python usage in this instance has worked for us, but well, if you want to keep using Python in the healthcare, there are some things that are not quite okay. It was recently established a Python healthcare special interest group, which is cool. It was March, and there was not so much activity later. Last edit of Wiki is on March, and we had less than 20 mail messages in 4 months. Last one being in April, so quite slow. And we need some community support because healthcare is a Java world. It's really Java world. And we don't have a real HL7 implementation in Python. We have a library that does part of version 2 and read-only, not writing, and not even a small piece of version 3, which is not acceptable if you want Python to work in this sector. And Mirth. Mirth is the software I talked to you about that does the translations and implements the Aichi stuff. It's made in Java, of course, and it's scriptable, but in JavaScript, using Rhino. Rhino is some sort of translation layer between Java and JavaScript. You can use Java classes from JavaScript. But why not Python and Jython? Because Python doesn't exist in this field. So what can we do? First of all, we must work together. I know that Python in healthcare is not very, we are not hundreds, okay? But there are some cases. This is one use case. Wesley Chan, which was there some minutes ago, has shown another nice one. And so we must just stick together and work together because we will never have an HL7 implementation, for instance, if you work everyone on its own. It's a very complex standard. And healthcare in ICT is very important, philosophically, and I think it's clear, but even economically, because it's a big sector, lots of money going in. It could be strategic for Python. And in the Western world, you know, the population is getting older. There's especially true in Italy, but in Japan too, for instance. So the investments are going to grow. And I think we need two things. We could use my first law of advocacy. We could do prototypes, for instance, for deploying already existing software. For instance, for Mirth. Mirth is configured using XML files. We at Search4, we're going to do some Python script to automate that part. So you just start to introduce some Python code inside the healthcare environment, and healthcare ICT professionals are going, oh, wait, this is nice. And of course, we should have a good list of serious use cases of Python in healthcare, because that's something the industry wants. We don't want to be the first to try it in such a mission-critical environment, but if you have, there's a threshold effect, you know. It's the same for technology adoption. One phone in the world, not very useful, even if you like yourself very much, but not very useful. Two phones could be useful if the other phone does not belong to some boring person. 20 phones are much better. 2,000 phones, 2 million phones, and everyone else starts to buy a phone because it's so useful. So we need to work on that. And allow me just last thought. I've been programming Python for the last 10 years or so. I've been doing multimedia, government, and ERP, CRM. And, well, I must admit, this field, I'm not being rhetoric, but it's special, because it has such a direct impact on people's lives. And it's doubly so if you can do it in Python. You all know why. So I'd like you as a community to help me to keep doing healthcare ICT in Python. Thank you for listening. And if you have questions of any kind, insults, no, not insults. Yes.
When you mentioned the reasons why you decided to use Python, you said that in the team you had people that weren't developers. Does this mean that these people read the code and write code, or how?
Yes, actually they do, like the example I gave you about mechanical engineers using Python to do stress tests. Because it becomes, you know, to learn Python for such a task, it only gets a few hours. But if you use Java, maybe it's more difficult. But our goal was not everyone will be writing code, but just we must have something that you can show, and they can get the general idea of is it okay if it works that way? If that part of the machine moves, then these other things happen. Python is quite valuable from that point of view. And I meant the large team, including our industrial partner and all. But yes, what I wanted what we wanted was people can read the code and have a general idea. What happened was people started to use Python to write the code, which is very cool. When I see non-developers using Python to do stuff, because it's quite easy to do, it's always nice. Other questions? No? So thank you for listening again.